going to
This
record
conference
this
will now be recorded.
so that people could watch it if they wanted to. In the meantime, can you start queuing your questions? I'm going to open up a couple of different things. I'm going to open up like the review packets 1 and 2, and I'll also open up the online quiz, and I can share those screens with you guys and mark them up. So go ahead and start kind of figuring out what. A few things queued. Dominic, I assume the Packers are playing. I hadn't really paid attention to that, so you'll have to have two things going on at once. Corinne's asking for a vector addition problem that we can see, and Marika is saying in the second review packet, can we go over 12 and 16? Let's start with those, and then we'll go back to Corinne's question. So let me turn on the screen sharing so that you guys can you guys should be able to see review packet number 2 on your screen, and you should also be able to have a video of both. Dominic's asking about questions. Let's get started. I'm going to move on to question number 12. Can you guys just confirm that you can see the screen so that I don't go too far? I think I'm sharing the screen, but I want to make sure that I can. Okay, looks like we're good. Okay, so in problem number 12 here, it says that a target lies around and that we have a 10-meter high building and a student rolls a ball off the roof. So, you know, this word horizontal is important. The fact that it's horizontal tells us the initial y component of velocity is 0. We're expecting the trajectory to look something like this, where the initial y component is 0 and the x component is known. One of the key ideas here is that they gave me that the height is 10 meters. Technically, that means my vertical displacement is negative 10 meters because it's downward. I also know that the acceleration is negative 9.8. I could use negative 10. That is permitted. The College Board says for all of the multiple choice questions and for keys on the test that you can use negative 10 without penalty. I like 10 sometimes because it cancels out conveniently. We'll see if it does in this case. Another little kind of side piece here is in question number 12, it says air resistance is negligible. You can also make that assumption. If it doesn't say that air resistance is negligible, you can ignore it. So we've got a couple things. Delta by A is 0, and they're asking us, you know, how fast does it need to be going to cover the 3 meters? By the way, everything that I'm writing here in this kind of red color is all in the y direction. And so I'll change the color of the pen and do the x direction analysis. In the x direction, we know that the ball in this case is not accelerated. So I can just use Vx is equal to delta x over time. And you know, they're asking me the horizontal speed that is necessary. So I'm trying to solve for Vx, and I know that the horizontal displacement is 3 meters. If I knew the time, if I could answer that question, I'd be good to go and I could answer the question. So in blue, I've set up the horizontal analysis. I just need to answer the time question. I need to figure out how long it's in the air, which means now I'm going to go back to the vertical, and that's going to be what I'm looking for. So I'm going to set up my first equation. Delta y is equal to VOYT plus 1/2 AT squared, where this whole first term is equal to 0 because the initial y component of velocity is 0. Austin, can you not hear this, or is the audio not clear? I don't know what kind of adjustments I can make on my end. Can you guys give me some feedback on whether the audio is working? Oh, okay. Glitching a little bit. Let's see. I have another Wi-Fi network. Let's see if it's on my end. Um, I'm gonna just keep moving. I tried switching like home networks on my house. Somebody's saying Connor was saying that he jumped off and then came back on, and that made the audio much better. So you might want to try that. Let's get back to the problem. So we have delta y is equal to 1/2 AT squared, and I can solve this for time by multiplying both sides by 2 and dividing by a. I get 2 delta y over a is equal to t squared. And so then I'll take the square root of both sides. So in this problem now, I have 2 times delta y over a. That gives me 2 times -10 over -10. And so the -10s cancel out, and I have the square root of 2, which is 1.4. So now I know the time that it's in the air, 1.4 seconds. And I can substitute that in, and I'll be in much better shape. Bear with me here for a second. All right. Okay. So now that I have the 1.4 seconds, I'm going to put that in here, and I'm going to have 3 over 1.4 seconds. You know, all the different times that are given, are a little bizarre. By the way, notice that they're in like non-decimal format. The time is just root 2. So if I had left that as root 2 here in the denominator, I would have that format for choice C. So Marika, make sure that I've answered your question for number 12. Let's take a look at 16, 22, and 28. All right. Question number 16 shows a graph of acceleration. I've recommended many times in class that you put your eye on the y-axis to make sure you know what kind of a graph you're looking at. This is an acceleration versus time graph. So the area, I haven't even read the question yet, I promise. The area that I've shaded in, the kind of triangular region here, is going to give me the change in velocity. So if I knew what the area was, I'm going to get the change in velocity. Now, here's one way to think about it. The area is length times, 1/2 base times the height. The base is time, and the height is acceleration. And so if area is 1/2 the base times the height, what I'm really doing is multiplying time times acceleration. That's really what the area is, time times acceleration. By definition, acceleration is the change in velocity over time, and therefore acceleration times time is equal to change in velocity. So it's not magic where this stuff comes from, the area under the graph being my change in velocity. So if I look at question number 16, I've kind of analyzed the shaded region, and then I read this question, and it's really satisfying to almost predict what's going to be asked. We're saying that we're starting from rest. The car moves in a straight line with an acceleration, and we were given the graph. They want to know what the speed is. Here's the critical word in this problem. Well, it's one of two critical ideas. The first one is that it started from rest, and that's because the area only gives me the change in velocity. So if I don't know how fast I started from, I don't know what my final velocity is. All I know is how much it's changed by. But since I started from rest, whatever my delta V is also my final velocity. Anyway, so the graph is coming through a little like mangled for me. Looks like it's got a height here of 5, and it looks like the base here, I don't know if I'm reading that. Looks like maybe the base is 5 too. So it looks like the area is 1/2 of 5 times 5. 1/2 of 25 is 12 and a half. So it makes me want to choose E. I can see that that's not the right answer here. So I'm wondering if I'm just reading the graph wrong. Let me erase all these pen marks and see if I can kind of read the scale a little bit better. It's definitely starting at 5, and then it looks like, oh, okay. So check out what I did. I made a significant mistake. The question is, what is the speed of the car at 3 seconds? This is a question that students will make too. And so it's not the area of the whole shaded region. It's just that section. It's just the shaded section from 0 to 3 seconds. For those of you in a calculus class, which I don't think very many are, this is what's called a definite integral. And so if this line here, bear with me on the calculus lesson, if that line is a function, then we can say that we're going to take the integral between the lower limit of 0 and the upper limit of 3 with respect to x. This is just for people who have seen that. That's really what we're doing. Nonetheless, now I'm going to kind of do this again, except I'm going to analyze this as like two separate shapes. I've got the kind of red triangle on the top. I'll call that region 1, and the lower region 2. I have to add those together. The region 2 here is 6, got a base of 3, height of 2. That's 6 units. And then this one starts at 2 and goes up to 5. So the height is 3, the base is 3. That's 9, but it's only half of that. So that's 4.5. And so that's where, I have to add those two pieces together, and I get the 10.5, and that's where choice D comes from. And that was something I almost got caught on, and I've seen these a lot before. I wasn't careful enough to make sure that I'm talking about 3 seconds. Thanks. And I can see that quite a few of you, once I got started on that, brought that up and said, hey, listen, we're talking about 3 seconds. So Dominic saw that, Reagan saw that, and that's great. So that's the answer to number 16. Let's move on. Let me get rid of these things. The next question was on 22, and then there was also a question on 28. So let's take a look. Here's 22. This is a question that feels similar to the airplane and the flares that we're dropping, except in this case, we have a plane. The plane is carrying emergency hay bales, and here's the side view of the plane. There's the propeller on the front, spinning around like this, and there's a hay bale here, and it drops the hay bales down. Now the plane is going to the right, and we're told in this problem that that it's moving at a constant velocity of 50 meters per second. So that's an important piece of information, 50 meters per second. And it drops one hay bale every 2 seconds. And we know that the height above the ground is 180 meters. So now we're being asked, how, like in question number 22, how far apart will the hay bales be on the ground? So let's ignore the falling part. If the first hay bale, I'll call that hay bale number 1, is left here, 2 seconds later, the next hay bale is released 100 meters away. How did I know this? Well, velocity is equal to delta x over time. So I can answer how far horizontally this is if it's moving at a constant velocity by just multiplying velocity times time, 50 meters per second times 2 seconds. You can kind of just think your way through this answer too. So yeah, the hay bales are all being, essentially horizontally fired, but they're all exactly 100 meters apart from each other the whole time. And so that doesn't change. And they hit the ground here, and they are, 100 meters apart. So hopefully that answers your question for number 22. 21 is, nobody asked that, but let's just kind of take a quick look. 21 says, as they fall through the air, what happens to the distance of separation? There's other questions that I've seen related to this with water drops that we did in class, or balls falling from a tower. But if one of the bales falls, if I were just to draw a motion diagram of the falling bales, we would kind of see that. We would see that the separation does increase. This distance between hay bales, 1 and 2 has to be smaller than the distance between 2 and 3. They keep getting farther and farther apart. And the reason is, and by the way, we did see this with the water drops and the strobe lights. Hay bale number, the first one that's released, which ends up being down here, the first one that's released is moving downward at some velocity. Let's say it's every second, just to make things easier. Acceleration is -10 meters per second. So that means when the hay bale that is released right after it, and it's released from rest, the hay bale underneath it is already going at 10 meters per second because it's a second later. And then 1 second after that, the lower hay bale is going 20 meters per second down, and the hay bale right above it is only going 10. And so therefore, there's always a 10 meter per second difference between the two. And so they're just getting further and further apart. So hopefully I've answered the question on number 22. Let's take a look at question number 28. And I think this one is one that we looked at in class. So make sure that you stop me if if you have questions. So in this one, we have, a traditional projectile, and you'll see that, that I drew it launched like this on level ground. And that's because they tell me this, it's launched from the ground and it lands 120 meters from its launch point. And then they say, it lands at the same vertical position. So I kind of know this profile. And we're told that this is 120 meters, and we're told also that it's in the air for 4 seconds. So if I did my kind of traditional stuff and separated horizontal from vertical, I could say that Vx is equal to delta x over time, and Vx is equal to 120 meters over 4 seconds. And so Vx is equal to 30 meters per second. So I know the x component of velocity. That's, kind of a big part of this problem. Keep in mind, by the way, that if I know the x component of velocity, we just found it, and I know the y component of velocity, I have the two components and I can kind of add them together, head to tail. Here's Vy. And so the actual velocity, the magnitude of the vector velocity V will be the hypotenuse of this right triangle. So if we can answer the Vy question, we know Vx is equal to 30. If we know Vy, then I know two sides of a right triangle, and I can use the Pythagorean theorem to find the unknown side, in this case, the hypotenuse. So it's not too bad of a problem. So let's go back over here to the vertical direction and see what we can figure out. Remember that on a long level range, delta y is equal to 0. So when I write out my initial kinematics equation, I'm writing out the first equation. I get delta y is equal to VOYT plus 1/2 AT squared. This is equal to 0. And then I'm going to subtract this term from both sides. I get negative VOYT is equal to 1/2 AT squared. Notice that one of the two t's on the right cancels out with the t on the left. And now I can kind of solve this for t, and it becomes negative 2 VOY over A is equal to t. No square root in this case. So I made a mistake. I'm not solving for t, I'm solving for VOY. So let's kind of take a different course here. So I'm going to multiply both sides by -1. And so I get VOY is equal to negative 1/2 A times T. So VOY is equal to negative 1/2 of negative 10 times 4 seconds. The negatives cancel out, and I get 5 times 4, which is equal to 20 meters per second. So now I know VOY, that's, actually, I should put it right there. That's this value, it's 20 meters per second. And I can use the Pythagorean theorem to solve for the magnitude of the unknown. Well, I have a calculator here and I could do it, but this is a good kind of idiot check. The hypotenuse has to be the longest side of the triangle, so it can't be A or B, because B is equal and A is smaller. And so I would have to, this narrows down to either choices C, D, or E. And if I just use the Pythagorean theorem, C squared is equal to A squared plus B squared, I can solve this problem. Make sure that I've answered your question, even though I didn't show you, the very end how to get answer C. Make sure that you get question number 28. I think that was Dominic's question. So I think I did get a question about acceleration. I think I went over that in the drops falling, the hay bales falling down. Let's see what else we have. So Ryan Farrell is saying, can I go over the question on the online quiz? It starts with a projectile is fired from a gun near the surface of the earth. And then somebody else is asking, just in general, why is it that an angle between 0 and 45 goes the farthest, despite that 45 to 60 stays in the air longer? And then Corinne is asking about vector addition. So let me answer the question about the 0 to 45. There was a discussion about that in one of the classes today. And that discussion that we had was very, very unique to the type of problem where it was fired from some angle. It fires from an angle on the top of like a cliff or something like that. And we found that an angle less than 45 degrees would yield a better result. But if we're dealing with a horizontal range, then 45 degrees, not, some random angle between 0 and 45. 45 specifically gives us the longest range. This might be a good opportunity to play around with an online PhET simulation. I'll show you how to get there in just a second. Sometimes you can really learn physics more intuitively using these tools. By the way, the one that I've drawn here is 45 degrees. So if I shot with the same velocity at 60 degrees, I'm going to get a much higher trajectory like this, but a lower range. Notice that the range shot by the blue trajectory, which we'll say was 60 degrees, is less than 45. And that's just a function of, its path. And then at 30 degrees, I'm going to get something that looks like this. And one of the things you'll find interesting is that 30 degrees and 60 degrees give you the same range, less than 45. 30 is in the air for the projectile fired at 30 degrees is in the air for the least amount of time, but it's got the largest the x component of velocity. So if I were to show the x component, the y component is quite small, and the x component is quite large for a magnitude v fired at 30 degrees. Whereas if we do this kind of same analysis for the blue one, we'll say that the y component is quite large, so it stays in the air for a long time, and the x component is quite small, which means that even though it's in the air for a long time, it's going so slow that it actually doesn't go, perhaps quite as far as it could, otherwise. So, this is nicely analyzed by using just kind of that way of thinking. I'd like to bring up a PhET simulation. So I'm going to change the screen that I'm sharing and kind of show you where you could go to just have some fun with this. Let me get rid of the things here. I'm going to change the application that I'm sharing. So you should be able to see. Maybe you can't. Give me a sec. All right. I think I'm now sharing, yeah, I'm sharing a browser. And so I'm going to go to PhET simulations. I just Googled this. I think that you guys have seen some of these in your other classes. And so I'm just going to, go to the physics simulations. And these are good to play with. I should do a better job of posting some of these on our unified classroom page. But there's a cool one on projectile motion, and you can play around with it in HTML5, which means you don't need to run like Java or anything like that. So Corinne is saying, is 90 in the air longer than 60? Yeah. And Corinne, by the way, this has a really cool feature where you can do some vector addition. So here's this cannon, and you can kind of change the angle. So let me send one at 45, and it gives us the option to like show components of velocity, and down here you can change the launch speed. Let's just go ahead and fire this thing. They changed it up a little bit, so I have to figure out where the fire button is. Why isn't it firing? Oh, and let's just fire it from the ground as well. So I'm going to bring this down at 45 degrees. I don't have to hit the enter button or space bar. All right, I thought I was hitting that already. Anyway, so we can kind of see that trajectory here, and then I'm going to increase it up to 60 degrees and fire it again. And you can see that this looks, somewhat similar to what I was doing before. Now I'm going to bring it down to 30 degrees. And it's a little deceiving. I'm going to bring up my markup tools here. It's a little deceiving because you're saying, hey, look, that one went farther. But when I was at the launch height's actually 2 meters here. So, this right here is the launch height. It's not quite a straight line, but like they do have the same range when I'm at that height. So, I don't know if this allows me to lower the cannon even more. Yeah, I think it does. So that would be the right way to show this. I'm trying to erase this stuff. I can do it. All right. So now I'm at 30 degrees. I fire it. Now I'm going to go up to 60 degrees and fire it again. Same height here. And then we'll see, obviously, 45 gives us the optimal range. And then, one last thing, if I erase these, if I show the components, the velocity vector components, this is something, you've seen in class, which is pretty cool to play around with. I'm going to go up to a much higher angle here. You'll see the total velocity vector 2 in that dark green. And we can show acceleration vectors as well. I just added that. That's the one in the downward direction. And then lastly, here's my 90-degree shot. So play around with this if you're interested and see if it's helpful in any way. By the way, I'm going to just click back here. And this is, I'm sure Corinne's not the only one who has a question on this. But if I go to motion, there's some really cool vector addition stuff that you can play around with. Let me find it. And so I'd recommend the one on projectile motion. This might be under math, but they have some really interesting vector simulations. I think I can search up here in this window. For those of you who aren't interested in this, bear with me. I'll be done soon. So this is a vector addition simulation. And so in this one, I can take one of these rays and it'll tell me, what the length is. And, so I can change the magnitude and it resolves it into the X and Y components. And then if I wanted to add another one, I could bring it in here. And there's a couple of different ways for me to show it. I could arrange it like head to tail, and it's going to show me the sum of these. So notice that the vector sum, the one in green, is from the beginning of the first one to the end of the second one. There's a couple of different ways of looking at these things in component form. So you can kind of just mess around with this, and it might help with adding vectors and getting kind of a better understanding of them. So that's it on the PhET simulations. I'm going to change my screen sharing and go back to the packets. All right, so we should be back to the packets. And I just want to make sure if people's questions are getting answered. Ryan Farrell has a question on the online quiz. I do want to look at that too. I think I've answered most of the questions. Corinne, yeah, 90 would have been in the air longer. And I've got 2 questions about from the online quiz. Let me do this. Let me just do one last question, number 18 on the first review packet, and then I'll go to the online quiz, and then it'll be a wrap. Here's question 18. From packet number 1. The trick to this question is that you have to answer the acceleration question first. So we have this inclined plane. The object starts here at time equals 0, and then it's going to slide down. It's going to be, let's say, here at time equals 1, and then way further down at time equals 2. And if this were really, really steep incline, we increase the angle theta to a much larger number. then the acceleration would be larger. We have to answer what the acceleration question is. So we know that from time 0 to 1 second, it travels a distance of 1 meter. So I'm going to call that horizontal displacement 1 meter. We're going to say that that time is 1 second, from 0 to 1 second. And we also know that the initial velocity is equal to 0. So I can answer the acceleration question by using the first equation. It's going to be delta x is equal to VOT plus 1/2 AT squared, where VO is equal to 0. And so I'm just going to solve this now for A. It's going to be 2 times delta x over t squared is equal to A. Delta x is 1 and t squared is 1. So I basically get 2 meters per second is my acceleration. Now I know what this is. It's 2 meters per second squared. So then I can answer the question, if it is accelerated at 2 meters per second, how far will it go in 2 seconds? I already know that this is 1 meter, but now I'm trying to answer the question, what's this distance from 0 to 2 seconds? So let's go ahead and do it one more time. Let me do it in a different color so we don't mix this up. So like part 2 of the problem is to say delta x is equal to VOT, this is still 0, plus 1/2 AT squared. And I'm going to plug in for a 2, and for time, I'm also going to plug in a 2, but I have to square it. So I get delta x is equal to 1/2 of 2, which is just 1, times 2 squared, which is 4, is equal to 4 meters. That means from the beginning to 2 seconds later, I've gone 4 meters. Well, I went 1 meter here, so that means then that the unknown distance from 1 second to 2 seconds is 3 meters, and that's how I get question number 18 as answer C. Let's take a look at a couple of the online quiz questions and see if we're in good shape. I'm going to change my screen back. There's got to be a better way for me to change my screen faster. I guess this isn't too bad. First world problems, right? Okay. So we've got, I'm going to bring the online quiz up. Okay, so the first one, I've got to change the screen again because now it's showing the wrong browser window. So let's see if we can figure it out. All right. Okay, so Ryan's question is, a projectile is fired from a gun near the surface of the Earth. Ryan, I'm going to bring this question up. Just make sure it's the right one. I think it's under 2D kinematics. So it looks like it's this one right here. So Ryan, just give me the nod that that's the one that you wanted to take a look at. Okay, so a projectile is fired from a gun near the surface of the Earth. The initial velocity of the projectile is a vertical component of 98 meters per second. So I'm going to go ahead and draw that out. I haven't read the question yet, but that's 98. And the horizontal component is 49. And they want to know how long it will take for the projectile to reach the highest point of its path. So I'm solving for time. I know that the initial y component is 98. How fast it's going side to side, or the x component, doesn't matter at all. So it could be going at half that or at 0. It just doesn't matter. So I'm just going to ignore that. It doesn't affect my results in any way. So the acceleration is equal to negative 9.8 meters per second. I don't want to get too sloppy, so let me put some units in here. The highest point occurs when the final velocity in the y direction is equal to 0. And I'm trying to solve for the time question. So it looks like the second equation will work well. I'm going to use K2. This becomes VF is equal to VO plus AT. I'm going to solve it for time. VF minus VO over A is equal to T. And final is 0. Initial is 98. And A is negative 9.8. And it looks like it's going to be in the air for 10 seconds. The negatives cancel out, and I get 98 over negative 9.8. And that's where choice 2 becomes the best answer. So make sure that I've answered your question, Ryan, on that particular online quiz. And then Connor says, a roller coaster traveling with initial speed of 15 decelerating uniformly. So that sounds like a kinematics in 1D problem. So let me see if I can find that. Looks like this is the one right here, question number 17. Well, it's question number 7 on mine, but it's going to be different for everybody's. So make sure, Connor, that's the one that you were talking about. It's traveling with initial velocity. I'm just going to write this stuff down of 15 meters per second, and the acceleration is given to us as -7 meters per second squared. And then it comes to a stop, so the final velocity is 0. And they're asking me how far. So they're asking about the vertical displacement in this problem. This is a great example of using the third equation. VF squared is equal to VO squared plus 2A delta X. And I can just solve this for delta X. I get VF squared minus VO squared all divided by 2A is equal to delta X. And now I'm ready to go. I'm just going to plug these numbers in. That's 0 squared minus 15 squared over 2 times -7. And 15 squared, I think, is like 225 divided by 14. The negatives cancel out. Technically, it's negative over a negative. And so if I've done this properly, I'm getting like 16.1. And so it looks like choice 3 is my best answer for that problem. Connor, make sure I've answered your question. All right, we're at the 45-minute mark. I think we're in good shape. I think that I've been able to answer most, if not all, of the questions. Dominic, best of luck to your Packers tonight. And if you guys have additional questions, feel free to see me in the morning. Tomorrow morning works well. Tomorrow afternoon doesn't work well. I've got another review session with the Physics C groups. That's it. Have a good night.